So our next adventure with our right triangles is taking this Pythagorean theorem and putting it into three-dimensional figures. So, we did a little bit of three-dimensional space in chapter 6 just briefly, but this is going to be something more common to you, something you're recognizing more often, and that's just three-dimensional figures as like pyramids and prisms and things like that. So we're going to see how can these triangles show up in more than just here's a triangle, right? So that's what we're looking for. Now, it says Pythagorean theorem in three-dimensional figures, and we are going to go back to using our regular old Pythagorean theorem, but always be on the lookout for those triples and the 30, 60, 90s and the 45, 45, 90s to save you some time. So even though it says Pythagorean theorem, you can still use your shortcuts if they show up. So really be watching for them. Now, before we get there, we probably need to do a little vocabulary lesson because you're probably not as familiar with these three-dimensional shapes. I believe this is the first time we've actually used them this year. So this first one is a pyramid. I apologize. I don't know what this title is on this slide. I'm so sorry about that. This is not a triangular prism. This is a pyramid. And in fact, we would name it based on the shape of the base. Now, I'm not sure if that base is a square or a rectangle, but it kind of looks like a square. So I'm going to make a tiny assumption here and just say square pyramid. But it could be a rectangular pyramid. We just need to know a little bit more information. But this isn't really about that. This slide is more about vocabulary. So again, when you have that single point on the top, it's called a pyramid, right? It's not a prism. So speaking of that single point on the top, that single point is a pretty special one and has an important name. That's what we call the vertex of the pyramid. So that point right on top is the vertex of the pyramid. Now, technically, all the points are vertices, but that one would be the vertex of the pyramid. So if they just say the vertex, they're talking about that one up there. All right. Now, do you guys know the name of that square on the bottom, that shaded in square? That we would call the base, right? And that's how we name a pyramid, is by the shape of the base. So this whole big shaded in square on the bottom is the base. All of these well, that's what I just spoiled it for you, but these segments, right? All the lines that are making up the pyramid, these are all called edges. Now, I probably should have started by saying, you are going to have to draw this in your notes, obviously. So pyramids are a little tricky to draw in your notes, but I would start with these edges here and make this front triangle. This is how I always do it. And then I kind of make my side triangles over here, kind of make this go back, make this side go back, connect it, and then connect across the back. So that's a way to draw it. If you haven't attempted it yet, that's how I would do it. But I'm sure you guys are better artists than I am. But every single one of those segments that I just drew in to draw that pyramid, that's called an edge. All right. All of these other flat surfaces then, like this triangle here, those are called faces. Right? So that is a face. So this pyramid has 4 triangular faces and 1 square face down at the bottom that has a special name called the base, right? Technically, the base is also a face, but it has a more special name, so we call it the base. So any flat surface in that shape, in any shape, is called a face. All of the lines are called edges. All right. So then there's 2 more special things that come along with pyramids. The first one is that we have this segment that is dropping straight down from the vertex, and it goes right down from the vertex down to the base. And it does, in fact, make a right angle with the base. So like if you made a line here that would connect, it makes a right angle right down there with the base. And that is what we call the altitude of the pyramid. It's also sometimes called the height of the pyramid, and that's kind of interchangeable, right? Altitude, height, coming straight down from the vertex right down, and it is hitting the very middle of this pyramid. And that means because we have, we always assume that our pyramids are standing straight up and down, right? Not leaning from one side to the next. And especially with a square pyramid, you know that it's going to come to the very center and be, all the same distance away because all of those edges have to be the same. But that is something that we can assume. Technically, that is called a right pyramid, is when it is standing directly up and down and not leaning one way or the other, but we really won't always say that. You will just assume that, and they will have to tell you if it's otherwise in this class. So the altitude forms a right angle with the base, and it drops straight down from the vertex and lands in the very center of the base. So the last special interesting line that's drawn into this picture that has a name is this one right here. So this one is also coming from the vertex and it's making a right angle, but it's coming down one of the faces, right? It's coming from the vertex and making a right angle with a base edge. And so it is forming that right angle on one of the faces. So this is actually what we call a slant height. It's technically the height of one of those faces, right? Or it's the altitude of a face, but it is called a slant height. So you see how it's kind of like the height of the pyramid, but slanted because it's on a face. That's where they came up with the name, I'm sure. All right, so vertex, face, base, edges, those are all common to, any pyramid out there, but also really any three-dimensional shape. However, altitude of the pyramid, that's going down the center, forming a right angle with the base, and slant height is the one that's coming down one of the faces and forming a right angle with a base edge. Those are kind of special to pyramids. All right, so the next three-dimensional shape that we're going to work on is a prism, right? So this one is a prism, and again, we name a prism based on the shape of the base. So this one looks like it'd be a rectangle. Again, we should probably have more markings to make sure that we know that, but that's not the point. This is more vocabulary. So you can see that shaded in part down on the bottom. That is the base again. Right? And then just like before, any of these flat surfaces, those are called faces. Oops, didn't mean to write with my highlighter. So notice the difference here. Now, a prism technically has two bases, right? It always has two bases. Here I have this one that's highlighted, shaded in, but it also has this second one right up at the top. So a prism always has two bases, but a pyramid only has one base, right? One up top, one down at the bottom. A pyramid only has one base, and it's always the side. I guess that was confusing where I drew the arrow to. It's always that flat surface that's across from the vertex is the base of the pyramid, right? So a prism always has two bases. Sometimes it's trickier to figure out which sides are the bases. On a rectangular prism, it actually doesn't matter. You can call any pair of sides the bases. The thing is, the bases are two parallel and congruent faces. So remember, if you think back to chapter 6, which I know we breezed through very quickly, but when we're in three-dimensional space, those flat surfaces, we call them parallel if they never intersect. So do you see how those two orange faces that I colored never intersect? So that's why I know that they're parallel, right? They're not going to meet, and they're congruent. They're exactly the same size. So those are, two parallel and congruent faces. I could call those two orange sides the bases. Now, I can't call this yellow face and an orange face the bases because they intersect. But I could say, oh, well, hang on. That yellow side and this yellow side over here, they never intersect. They're parallel and congruent. Yeah, you could have called those two the bases. So it just doesn't really matter as long as they're two parallel and congruent faces, but you got to pick a pair, and that's what we're going to call it, right? Now, some prisms are a lot more obvious. If you had a triangular prism, for example, a lot of times you'll see them kind of like this. See if I can't draw a triangular pyramid here, or prism, excuse me. Right, this one would be solid. Okay, right, so on this one, it only has two faces that are parallel, and congruent, and that is these two triangles, because all the other faces intersect, right? So those have to be the bases, and so that's why we would call this one a triangular pyramid. All right, so that was a big discussion around a little bit of vocabulary, but it is kind of important stuff so that you know which sides you're calling the bases, right? All right, so we have bases and we have faces. We also have edges, just like we did with our pyramid, right? So those are all the segments that you would use to draw your prism, right? Those are all edges. All the way through here. Those are all edges. And then we have these two really special. So there's two segments left that are pointed out in this diagram that are special. So again, faces, bases, edges, technically vertices, all those corners are vertices. Those are common to all three-dimensional shapes. These two are special for our rectangular prism. Actually, I should say any prism. But I see that I have this pink line drawn in, and I have the red line drawn in. Now, if you notice, the pink line is technically a diagonal of that bottom face, right, the base. So that pink line is called the diagonal. Actually, it is called, the base diagonal. Right, so this pink line here is the diagonal of the base, you could call it that too, or the base diagonal. Now the red line isn't laying flat on any of the surface. That red line is slicing through the center of the entire prism. So this we would just call the diagonal, or the diagonal of the prism. I apologize.
Head to the choir room.
All right, sorry, choir students.
Head to the choir room.
Okay.
Thank you.
So this diagonal that's slicing through the entire shape, sometimes they'll just say it's the diagonal, but they mean it's the diagonal of the prism. It's not laying flat on any surface. Otherwise, if you have a diagonal drawn in on one of the faces, it's either a face diagonal or a base diagonal. Most often it's going to be the base that's drawn in. So those are the special things there for your prism. Okay, so how do I use this, right? Maybe as you're kind of seeing how these things are drawn in, you're noticing some triangles popping in there. But if not, let's do some practice problems here. So here this first practice problem says the dimensions of a rectangular solid are 3, 5, and 7. Find the length of the diagonal. So when it says a rectangular solid, this word solid really is telling us that we're talking about a prism. That's kind of some weird vocabulary that some of the math textbooks and things use, and I wanted you to just see it in case it pops up at some point. So whenever they say it's a solid, they're talking about a prism. So it says that our dimensions of this prism are 3, 5, and 7. We need to find the length of the diagonal. So let's start by sketching a picture. So I know I have a rectangular prism, right? So this is my fastest way to draw a rectangular prism. And then I drop these down. I know everybody kind of has a different way to do it. That's how I have it. Again, sorry about the bell. So the dimensions are 3, 5, and 7. Now I get a lot of questions about this. How do you know where the 3 goes, the 5 goes, and the 7 goes? So let's say I drew my picture. I drew a rectangular prism, right? Random rectangular prism. So looking at how my picture is, I would say, okay, that kind of looks like that's the 3. And I'd say this kind of looks like it's the 5. And then the long one would be the 7. We say, but doesn't it matter? Does it matter, right? And the idea is we are trying to find the length of the diagonal, right? Diagonal of the prism means it's slicing through the entire prism, right? Not laying flat on one of the faces. So that's what I'm trying to find. Now, when I get that question, does it matter which way I go? Well, let's just picture this. What if I took that same prism and I rotated it so that a different side was the base. So something like this. Okay, now I still have 3, 5, and 7, so let's say this is still 3. This one would be 5. This is 5, and now my height is 7. Does it change the length of this diagonal that's slicing through here? Sorry about that, guys. Technical difficulties. Is that diagonal a different length? Absolutely not, right? All I'm doing is taking the exact same prism and I'm turning it around. Whichever way you want to turn it so you can draw it, it's the same thing. So it doesn't matter where you're putting those dimensions, you'll use them all eventually, no matter which direction you do it, okay? So I'm just going to take this top one and we're going to rock and roll with that. So I'm trying to find the length of this purple segment, right? I don't think I can start with that because I don't have everything I need. In fact, I can't even really make a triangle yet. But if I try to make a triangle, I really would need this segment drawn in as well, right? Are you seeing that triangle now? The triangle would be this, this, and this, right? Now, how do I know that it's a right triangle? This is a rectangular prism, right? So I have right angles in all of those corners. So I have a right angle here, right? The base is a rectangle, so I know that I have a right angle there, one up here, one down here, technically, right? All 4 of those are right angles on the base. But I also know that it's standing straight up and down because these would be rectangles as well, right? So I do have a right angle right here. You must draw in your right angles because you cannot use the Pythagorean theorem without a right angle. So make sure that they're drawn in your picture. You have to draw them in. Because I'm seeing, okay, well, do I know that the lengths of that yellow triangle that I highlighted? Well, hang on. I do know one of them, right? This side here is the same as this side here. So that must be 5. Oh, but I don't know this base diagonal yet, right? I don't know that, so I need to figure that out. Are you seeing the second right triangle that formed when I marked my right angles? I've got the side of 7. Oh, I know that this side right here is 3, and I have a right angle. Y is across from the right angle. So Y is our side C here. 3, 7, Y. Is that a triple? No, it's not. Shoot. Oh, well, that's okay. So I can do my Pythagorean theorem here. 3 squared plus 7 squared equals y squared. And I can solve for y. So let's see. That gives us 9 plus 49 equals y squared. 9 plus 49 is 58 equals y squared. 58 is not a perfect square, but that's no big deal. I'm just going to call this the square root of 58. Y equals the square root of 58. Why am I not worried about reducing this? I'm not worried about reducing it because I'm not done yet. That's not my final answer, right? I'm not trying to find y. I don't want the base diagonal. I want the diagonal of the prism. So I'm just going to leave it like that and work with it a little bit until I get to my final answer. And if I still have a radical at the end, that's when I'm going to reduce it. So now I can have everything I need to go to my yellow triangle that I wanted, right? So again, that x is across from the right angle, so x is c, right? So I have 5 squared plus the square root of 58 squared equals x squared. So I had to do the Pythagorean theorem twice. I had to make 2 different triangles to get to what I want. It's okay. You're going to have to do that in prisms. But I know what I'm doing, right? And if one of those was a triple or both of them, way faster, right? But it's not in this case, and that's okay. So here we go. Let's see. I have 5 squared is 25. Square root of 58 squared. Ooh, do you see why I didn't reduce my radical? Super easy. That just gives me 58 equals x squared. Now I am going to, let's see, 25 plus 58 gives me 83. right. Square root both sides. Ooh, square root of 83. I don't think that I can reduce that. I believe 83 is prime. So this is going to become x equals radical 83. Now technically, again, plus or minus radical 83, but it is a segment length, so negative doesn't make sense. So my length of my diagonal is radical 83. Even if they're not beautiful Pythagorean theorem numbers, it can still do it. But the trick with prisms is that you're probably going to have to do the Pythagorean theorem more than once. You got to find that diagonal of the base and then use it to find the diagonal of the whole thing. But watch for your triples because a lot of times they'll show up in there. Awesome. All right. How about a pyramid then? So again, I know this takes a little bit to draw. However you're getting the idea of drawing, again, the way I usually do it is I start with this front triangle. I draw this, then I draw down the side over here, connect, and then parallel, connect what's left. Mine never show up beautiful, so do your best. Okay, so here is our problem. It says this is a regular square pyramid. So again, regular kind of telling us that it's standing right up and down, also telling us that the base is square. It's kind of redundant, right? So this is a square pyramid, which tells us that all of these sides down here are congruent and all the angles down there are right angles as well, right? Just in case we need it. It says the perimeter of the base is 40. The perimeter is 40. If the perimeter is 40, how long is each side? Well, there's 4 congruent sides if it's a square, so each side would be 10, right? Cool, then we just found our side length. And it says segment PM, that's this one right here, segment PM is 13, so that is an edge. It says find the length of the altitude. So remember, the altitude is the segment that drops straight down from the vertex, goes to the very middle of the base, and it makes a right angle with the base. Ooh. See if I can draw that a little bit. There we go. It makes a right angle with the base, right? So that is the same thing we're trying to find right here, x. Okay. Again, I don't have a triangle yet, right? What I'm missing to make my triangle is this segment right here. Do you remember what that segment is called? That segment is called the slant height. All right, so let's see, what do I know then? Well, I know that this altitude drops to the very center of the base, and I know that a whole base edge is 10. If this is the very center of the base, then this must be 5, right? Because if it lands in the very middle and the whole thing across is 10, then it must only be 5 to get to the edge. I also know over here, since I have my isosceles triangle, that this is landing directly in the middle, right? So these are both 5 over here too. I don't know my slant height yet though. So the triangle that I want to use to solve for x that I'm trying to get to is this yellow triangle, but I don't have enough information yet. I don't have any angle measures. I don't know 30, 60, 90, anything like that. But when I marked all my right angles, like you absolutely need to do, did you notice this second right triangle that came up? Oh, all right, 5, y, and 13. Notice that the 13 is the side across from the right angle, so that's C, 5, y, 13. That's a Pythagorean triple. Pythagorean triple. I don't know why I put that in parentheses. The Pythagorean triple, 5, 12, 13. That 12 is the one that we were missing, right? So y equals 12. So that's 12 right here. Sorry, right there is 12. So I know that side now, and I use my triple. Now, if you didn't see the triple, yes, I guess you could write out the whole Pythagorean theorem on that one, but come on, look for those triples. So now if I look at my yellow triangle, I have 5, x, and 12. Careful. Is this another 5, 12, 13 triangle? No, because the 12 is the hypotenuse this side. That's why it's crucial that you mark your right angles and you're really paying attention to which side is the hypotenuse. So this one is not the 5, 12, 13 triple, so I can't just do a triple again. This time I gotta write out my Pythagorean theorem. So I have 5 squared plus x squared equals 12 squared. And now I just go ahead and solve with the Pythagorean theorem. 5 squared is 25 plus x squared equals 144. I subtract 25 from both sides. I get x squared equals 119. Square root. Oops, I already used that. 119, you cannot reduce that, I believe, is prime. So my answer is the square root of 119 meters, right? Again, technically plus or minus, but side length, so I know it's not negative. So my altitude of my pyramid is square root of 119 meters because I know my units here from the problem. All right, so again, more than one right triangle happening. Mark those right angles, right? And draw out what you feel like you want to have to make your right angle to what you're getting for. Sometimes you don't have enough information, so see if there's another right triangle hidden in there that you could use to get there. Watch for your triples.